In this video, we'll discuss how to plan, conduct, analyze, and report on the results of an implemented experiment. So there are several steps that we talk about and tend to go in order with a couple of exceptions. But the very first thing that you have to do when you're planning an experiment is to recognize and state the problem. And we'll go into each of these steps in more detail in the next slides. Next, after you've identified the problem, you have to pick out the variables from the problem and select the different factors, levels, and ranges that you'll be utilizing. You also have to choose the response variable, and steps 2 and 3 really do go together and can go in either order. Step 4, choice of design, sometimes students think can also go in any order with 2 or 3, but actually the choice of design really does depend on the factors and response variables that you're using, so you really do have to select your variables before you can select the appropriate design. Step 5 is the conducting of an experiment, and this is what people think of as doing an experiment. You have the person in the white lab coat who's actually running the experiment. So that's step 5, is actually doing the implementation part. Step 6 is doing the statistical analysis, and this is a much bigger step than most people understand, and we'll talk a little bit more detail about why that is. And then step 7 is drawing conclusions or recommendations from the results of the analysis, and again, that is also a bit of a bigger step than many understand. So step 1, recognizing and stating the problem. So there's several different ways that we can do this. Factor screening is a way that we can do this, a particular type of problem, and looks at what has an impact. So what are the what are the variables that have an impact? What are the factors that have an impact? Optimization says what are the best conditions that we could possibly have. Confirmation tests a theory. Does the theory hold? Discovery, what are some new factors? Now this is very similar to just the regular old factor screening, but in discovery, factor screening seeing what's impactful. Discovery is trying to determine what are new variables that I haven't even considered. Robustness, under what conditions does the process work, or what are the bad conditions? In robustness, this says if the outcome is similar enough to different levels of a factor, then the outcome is robust to changes in that factor. So for this, obviously for robustness, we need to define similar enough. We can also look if the outcome is more robust to changes of a variable if we're at certain levels of another variable. So for example, does the quality of teacher impact math score? So that might be, is a math score improvement independent of the teacher who's implementing that curriculum? And then we can also determine, does that depend on the socioeconomic status of the student, which could have an impact here too. When we're selecting our variable, we really have to be careful about how we measure what the outcome is. So you need the idea, that's part of the selection of the problem, and of course the conceptualization of the problem isn't just selecting between those types of questions that we talked about in the last slide, but also actually being really specific about what is the question that you're interested in. Those are just some avenues that you can pursue and think down. Those aren't really the answer for you, just a couple of starting places. But when we're selecting the response variable, it's really important to identify very precisely what it is you want to measure and how you want to measure it. So this is a question not many people think of, but think about if you're measuring somebody's intelligence. How do you measure that? Well, that's a rather difficult question. The process of determining a measurement instrument for what we call a construct or an idea that isn't well defined in terms of a metric is the process of operationalization. So IQ score would be an operationalized definition of somebody's intelligence. But that doesn't mean that somebody's intelligence is exactly IQ score. That just means that's one way in which we've operationalized intelligence or made it into a number so that we can assess it. Now, as we've discussed in a previous lecture, we need to identify the level of measurement because this informs the analytic approach and the different assumptions that we're going to have to make. So not only do we have to identify how we're going to measure it in terms of the operationalization, but we have to identify the level of measurement of that particular operationalization so that we can select the most appropriate analysis and determine what assumptions we're going to have to check. A last thing here that we're not really going to dive into but is worth mentioning is that we need to have a reasonably reliable measurement and statistics in many brands of traditional statistics. I'll even say almost all. There's a particular group of stats that don't do this, but we assume perfect reliability of measurement. Structural equation modeling doesn't necessarily assume that, though it does make some other assumptions. But it's very common for us to assume that all measurements are perfectly reliable. That is, well, that the IQ score is the IQ. So reliability of a measurement, how well does it relate to, it's actually the validity of a measurement, but how well does it relate to the underlying concept that we're talking about? And more specifically, how precise is that measurement about that? That's more what the reliability is. So if we're using an instrument that's very noisy, that is, some days you may score a 50 on the IQ test, some days you may score 150 on the IQ test. Well, a change in 10 on IQ might be pretty meaningless if the measurement itself varies so drastically just based on a random day. So it's important to realize that all of our statistics assume that the measurement instrument is perfect and that limitations here inform or create very large limitations on the interpretations and conclusions that we can draw. And it's also important to realize, again, it's just something that we don't very often talk about. So if you ever hear people talk about statistical analysis, it's very likely, or designing an experiment, it's very likely that the reliability of the measurement is not something that they'll take into account. All right, so choice of factors, levels, and rates. So for all factors, controllable and uncontrollable, we need to look at what are the factors, what are the levels, and what ranges are we going to do. So factors are either manipulated, held constant, or controlled. So manipulation is like the independent variable where we're changing the levels of the independent variable for the different experimental units. Held constant is kind of like excluding people. So let's say in my study, I'm doing a study between math and IQ score, math ability and IQ score. But I know that gender is going to be an issue. So what I might do if gender is going to be an issue is select only one of the genders to be included in the study. So I'm only going to do my study with, let's say, females, and I'm going to exclude everybody else. So that would be a factor that is held constant. And we do this very often in experiments. You'll hear of, the white coat in the clean room and the, sterile environment. We're trying to hold everything constant between our different trials of different experiments under different experimental conditions. Statistical control is something that a lot of people think sounds really cool, and it is really cool. It's just not typically as powerful as we would like it to be. It is helpful when we can't control a factor, but it's really only a valid approach if random assignment is used. So statistical control is going to be like ANCOVA. It's an uncontrollable variable that we include in the model as a covariate. Now we also need to make sure we're including details on how the factors will be measured. We talked about operationalization with the dependent variable. Operationalization is just as important with the independent variable. How are you measuring the independent variable? What level of measurement are you using? And how are you going to code that particular type of variable? Are you going to call the groups group 1, group 2, group 3? Are you going to write a text string for each group name? How are you going to indicate that to the computer? That's all very important information. For things like levels of measurement, as we mentioned in a previous lecture, impact the analysis not only with the dependent variable, but with the independent variable. So it's really important that we can identify what level of measurement our factors are and how we are going to account for that. Again, because typically we have control of manipulated factors, very often the level of measurement will be, for our intents and purposes, nominal. And in a previous video, we talked about how when I'm baking cookies, I'll set the oven at 200 degrees, 300 degrees, and 400 degrees for my experiment. Though oven temperature is technically a continuous variable, and technically it'd be an interval variable because there's no true zero there. In that treating of the variable where I just have three groups and I'm not looking at them in an ordered way, I'm just splitting between the three groups, that is treating that variable, as far as level of measurement goes, as a nominal variable where we are using categories. So it's important to acknowledge that. And actually, if I were writing that variable up, what I might write is, though temperature is an interval variable, for this experiment I'll be treating it as nominal because I'm just using the three groups. And that is extremely common in design of experiments to use that approach. The choice of design depends on several things, but it largely depends on the conditions under which the experiment is happening and on the variables that we're studying. So choice of design is not just choice of statistical design, but choice of the actual design technique that we'll use in this course. Do I want to use a 2k factorial design? Do I want to use a fractional factorial design? Do I want to use a randomized complete block design? These are types of designs that we'll discuss in this course. And again, this component's largely what this course is about. So it includes the methods, but it also includes the analysis. It includes the software. It includes the code that you're going to write and what program you're going to write it in, what package you're going to use. So the software might be R. What package are you going to use in R? It includes your nominal type 1 error rate, and it includes your sample size. So all of this is encompassed within this choice of design. Now, what's really interesting is after you select the design, you should know, okay, and before this, you should know what all your variables are, what all the levels of measurement are, exactly how they're going to be measured, exactly how they're going to be recorded through the experiment. Here, you will know the experimental method you're going to be using, you'll know the analysis you're going to be using, and the assumptions of the analysis you'll be using. You'll select what software you'll use. So I'm going to use R. I'm going to use this particular function in R to do the analysis because I already know what analysis I'm going to do. I'm going to know my type 1 error rate. So when am I going to reject or fail to reject the null hypothesis? I'm going to know the sample size that I'm going to have. So actually at this stage, you should be able to write all of the code for your analysis. Because you have all of the things that you need. If you know exactly how the data will be structured, exactly what the variable names are going to be called, exactly how the variable data is going to be formatted, you can write the code. And actually, this is an extraordinarily useful skill. Right now, I'm working for a client where we are doing this and charging lots of money to write code ahead of time for them. And they're thanking us a whole ton for doing that. It's a really, really, really useful skill to have. But think about how you do this. What I would do is I would set up a data spreadsheet. If I'm collecting my data in Excel, an Excel spreadsheet, I would have the different column names, how I would have them. I would type in maybe a sample data entry, maybe a few sample data entries, and then I would go and write all of the code that I would use to analyze that as if it were real data. Now that doesn't mean you can write the conclusions. I obviously can't make the conclusions until I have the real data. But does it mean I can't write the code? No, of course not. I can absolutely write the code without making conclusions based on the code. So I could absolutely, with an Excel spreadsheet formatted like that, write all of the code that I'm interested in and then use it to prepare for the next stage that I'm looking at. So again, at this choice where you're choosing the design, and this is much further ahead of time. Sometimes this is years before the study ever runs. You can write all of the code such that all that you need to do when it's time to analyze the data is drop the code in. I mentioned this, I cannot overstate this, and I highly recommend maybe for your experiment giving this a shot. Maybe not for the first experiment because that's a bit of work, but maybe for the next experiment, try giving this a shot. I'll say that in previous times when I ran this course, I have required this. I guess you'll have to see the parameters for this course to see if it's going to be required for our class. But even if it's not required, I encourage you to give this a shot. Try at this stage in your experiment, writing it all out. And if you can't, then realize that something is missing. Either your variables haven't been well defined, or your methods aren't defined, or your analysis isn't. Think about what is holding you back from doing all of this. From writing the Excel spreadsheet with the exact variable names, writing in a few example pieces of data, or example observations that are going to come out of the experiment with the example independent variable factor levels for that particular experimental unit. And again, if you can't write such an example spreadsheet, then you haven't met and gone through the steps to complete this step yet. If you can't write an example spreadsheet with how the data are going to appear, then it's time to pause, figure out why you can't do that, and then go back and fix that. Not that you should make up data, right? This isn't saying that you're going to keep that data, but if you don't know the data well enough, and if you haven't designed the experiment clearly enough to be able to identify all of the different pieces of data that are going to be output from your experiment and everything that you're going to track and how you're going to track it, then you should pause, get that ironed out before you continue to the next step, which is actually performing the experiment. So performing the experiment is surprisingly anticlimactic. We do a lot of work before this. Performing the experiments is just where you actually do the experiment. You just kind of do what you said you would. Now, I will say that one trick with performing an experiment is to run a pilot test. Now, all a pilot test is a few runs to do quickly, just to try out your methods. And what this can be really useful for, I was mentioning in the previous slide, if you don't have enough information to be able to write all of those components and you're not quite ready, a pilot test is just kind of a run through. It's a quick run through to make sure that all of your methods are working well, that everything's coming out how you think it's coming out, that everything's going how you think it's going. And so I might run, 2 or 3 experimental units, or 2 or 3 trials of my process, and see how that works. Incidentally, that also gives me the data that I was talking about in the previous step, and you can absolutely use pilot data in the previous step before you perform the actual experiment to make sure that all the kinks are ironed out, and I would highly recommend doing that. Again, I mentioned it here, but they can be very, very, very useful before committing to running the experiment, and especially if you're kind of going against the recommendation we made earlier about doing sequential experimentation and you're doing one large comprehensive experiment. Pilot tests are invaluable to make sure that before you start the comprehensive experiment, you're ready to go. They have other uses. We may talk about them at the end of the next chapter, a couple of the other uses, but for now, I'll leave it there and just mention that pilot experiments are pretty useful for designing the experiment and getting everything ready to make sure there's no hiccups when you're performing it. Now, after you have your experiment run, then you have a whole bunch of data and you need to analyze the data. That's where statistical analysis comes in. However, the first step of statistical analysis is something that so many people forget about, and it is cleaning the data. Data cleaning is a huge piece of analysis of data. And in fact, I tell my clients 90% of my time is going to be cleaning your data. Because once I have your data and have cleaned it, it is very, very, very easy to run the analysis. And interpretation isn't particularly difficult. What it really is that takes so much time is getting the data in the format to be used. And actually, that's all data cleaning is. Data cleaning isn't like taking a scrub brush and soap to my computer screen. Data cleaning is organizing and formatting data in a format that it can be read in by the statistical software. So data cleaning literally is formatting data and reformatting data, and that is a very, very droll thing to do. It's not particularly fun, but it's honestly one of the things that we get paid for, that I get paid for, is to clean data, and to be knowledgeable and skillful enough at cleaning data that I can do data cleaning procedures that other people can't do, and can write code to do data cleaning that other people can't do. Now for the analysis, if in step 4 you had the code, or you had your steps well enough to write the code and did it ahead of time, for this particular step, all you have to do is drop in your data and hit enter. You've already written all of the code, so it's kind of all done. If you didn't do that, if you were just ready enough to do that but didn't actually do it, now is when you would write your code, you'd run your analysis, do your checks of assumptions, and all the other things that you would do and have been taught to do in a more traditional statistics course. Now, don't forget, sometimes I feel like students forget about graphics, but statistical analysis is not just numbers, it's also graphics. Graphics and numbers are a huge part of statistical analysis, and in explaining results to a client, I find that graphical methods are much easier for them to understand and visualize. Now, depending on what you've seen in your previous courses, don't forget these interpretation steps. And actually, if you think you've seen something different, previous courses, come talk to me, because this is how you should interpret every time with every type of analysis. First, the very first thing you do after data cleaning when you're analyzing data is check your assumptions. You do not run your statistics until you've checked all of the assumptions for that statistic and that it's passed all of the assumptions. Only after it passed all the assumptions do you move on to running statistical tests and creating graphics that summarize that. Graphics sometimes you can do even if it doesn't pass the assumptions, but you have to be really careful about the conclusions you draw. And then third is, of course, the conclusions that you can make based off of the graphics and statistical tests that you ran in this step. So for conclusions, it's important to remember that this sequential approach, if you're taking that, means that conclusions aren't necessarily the end of the experiment. Sometimes you can suggest follow-up runs or different factor level combinations that maybe are worth more study or more looking into. Again, this iterative approach allows you to create suggestions or edits for the next run such that it can improve every time and your final result is better. But as we've spoken about in previous videos, remember that as you edit the methods, as you edit the factor levels, you can't then combine those results with the previous results. So if you're making edits, this affects your ability to aggregate or combine your data. And ultimately what this ends up doing is reducing your sample size. So just be a little bit careful about it. So the American Statistical Association provides an acronym, ATOM, for how we should approach interpretation and conclusions. First, accepting uncertainty. Realize that we never prove something. All that we do is provide evidence for. And I think providing evidence for is a bit of a better term than suggest. We don't just suggest, we do provide evidence for. We use data to provide evidence for conclusions. But it is all within a realm of probability, which is why something isn't proven. It is just very, very, very likely or very, very, very unlikely. So be very careful when people say statistics proved or this research study proved. And this isn't to say that no research can prove anything. Mathematics research proves things all the time. Some theoretical statistics and theoretical physics research prove things all the time. But when statistics and statistical distributions are involved, when statistical tests are used and hypothesis testing, when confidence intervals are used, we don't prove things, we provide evidence for. And it can be very strong evidence, but it's important to acknowledge and understand the difference and accept the uncertainty that there isn't a proof, there's just evidence for or evidence against. You should also be thoughtful. So the A in ATOM stands for accept uncertainty. The T stands for being thoughtful, to think about what you're saying in the context in which you're saying it. It's really, really important to continue to consider how the experiment went and to reflect on that and how it impacts the conclusions that you would then make. Tied with being thoughtful is being open. So while you're considering this, don't try to hide the things that went wrong and sweep them under the rug. Bring them out into the open. These are things that should be discussed and debated and should be things that are incorporated into a research paper. Many researchers are tempted to be unethical in the sense that they really want to hide everything that went wrong. And again, the goal of research and the goal of the process of research is to be open about the things that went right and wrong so that future researchers can learn from both your successes and your failures. There was a recent study out that demonstrated that a large number of published articles in psychology couldn't be replicated. And that was a huge problem. What do you mean? The research couldn't be replicated? They made conclusions that in future studies would not have been supported. Well, what could have happened? Well, there's a whole ton of things that could happen. But one of the things that could have happened is that the researchers in the original studies could have been really tempted to say, well, we want to advertise our successes and hide the failures, which is a recipe that breeds ignorance ultimately. It breeds ignorance in the sense of the things that we thought we would have learned from your study, we now have to question because we don't feel confident that we can interpret it in light of what actually happened. I say something to clients sometimes that goes along the lines of you can do whatever you want as long as you tell everybody exactly what it is you did and why. And that goes along with this axiom from the American Statistical Association as part of the ADAM acronym, the O component, which is being open. The final conclusion, recommendation for conclusions from the ASA is being modest. Because we have to accept uncertainty, because we should be thoughtful about the context in which our study happened, in which we can interpret the conclusions, because we should also be open and acknowledge that not everything goes perfect. In fact, things very, very rarely go perfect, and that's okay, and we need to be open about the imperfections. We should therefore be very modest in our conclusions. There's no reaching for the moon, no trying to see how far we can stretch an implication. If you did a study, and a small study with a small sample size in rural Pennsylvania, the results of that study should not shake the world. Right? If you're doing these massive studies across the world, then that's something that could shake the world. But the fact that you noticed a pattern among people in a small and relatively isolated location, that should not be a study where you make sweeping conclusions about everybody on the planet. You need to be much more modest in the conclusions. And this is a really, really important takeaway that many statisticians, experimental designers, and researchers in general are being asked to reflect on. So overall, as we've mentioned, get statistical thinking involved early. You want to be involved early in the project because you don't want to give the post-mortem. What you want to be able to do is help to design a project that is going to be really thoroughly thought out and well planned from the very beginning. And don't just lean on your statistical knowledge. I'm amazed at how often I feel what I do is just logic, just being pointing out some potential logical flaws and pitfalls and being ready and willing to deal with them and to figure out how we can approach them. This goes with the American Statistical Association recommendations about being open. And I've found that sometimes people really don't want to acknowledge potential flaws that could happen, and just being open about those potential flaws, far from taking away from the study, if we acknowledge the potential flaws while we're planning it, can sometimes allow us to work as a team and collaborate to build solutions that drastically improve the quality of the study that we make. Planning the experiment ahead of time, that pre-planning steps, the steps 1 through 3 and even 1 through 4, when we're putting it all together in step 4, are vital to the success of an experiment. It's so important that you take the time to do those, to flesh them out. And again, they should be done thoroughly enough that you could create an example spreadsheet without having any data in front of you. You know your variables, you know the setup, you know the output that thoroughly. And again, to the extreme case, you should be able to write all of the computer code for the analysis ahead of time. And if you're missing something in there, go back and check. And I'm not saying you always have to write the analysis code ahead of time. I am saying that in order for it to be a well-planned experiment, you should be able to. And if there's something that you're missing that doesn't allow you to do that, you should pause, go back and look at it to figure out what that is. So again, just thinking through experimenting sequentially, using that sequential method to allow you to build as your experiment goes on and to make adjustments if things go wrong. A pilot study is also a great recommendation in there. And then keep it stupid simple. Really keeping it as straightforward and simple as possible is a fantastic way to make sure that things don't go wrong while you're doing the experiment, and that you can reach the conclusion stage with as much fidelity and validity through the process as possible. So this ends our discussion in design of experiments, our introductory discussion. On our next video, I think we'll go into R a little bit, discuss a few of the details, and I think you'll probably have your first project assigned after this video. So I wish you the very best of luck on that. As always, contact me if you have any questions. But otherwise, we'll see you in the next video for our demonstration.